He spent time at the University of Leipzig before he went to the US. He's also the winner of the Carl Scheele Prize, I believe, and is well known for his work on first-order phase transition as well as finite size effects. So I'm absolutely delighted that we have the second part of the talk from Christian.
Okay, so I'm very happy for the invitation. As I said, as Jennifer said, this might be a little too much abstract mathematics, so maybe we should have come for the first talk, but unfortunately, first conference here, but we couldn't make it. There's a little bit of dynamics in this if one sort of reads it right. So the motivation for the second part is, Jennifer already mentioned it, assume I'm sort of given LinkedIn today and I'm supposed to predict, right, they just joined Microsoft 2 days ago, approved by the European Union, and now they ask me how we will look in 5 years. We expect we have grown to double the size. Give us an idea how we might look. And related mathematical questions are sort of, well, to answer such a question, you want to sort of determine a statistical model for your network. Then you want to estimate the model from this one sample you have of LinkedIn. And then you want to generate a new model from that. And you may also want to ask, can we do that in a way which doesn't reveal too much information of everybody else, because who knows whether the Russians read my Graphon, and maybe I don't want them to know that much about me. So, I mean, Clinton should have done her stuff differentially private. She would have had no problems. Okay, so Jennifer gave you these directions, how out of a graph you get a limit which just replaces the vertex set by some measure space, and the adjacency matrix, which is the symmetric function on the vertex set, by a symmetric function on this measure space. And so I will tell you how you actually can get in this direction a random graph model and how we estimate it. Okay? So I will review a little bit what's known in dense graphs. I will talk about exchangeability, and then I will give you models for sparse random graphs, and then I will want to talk about how to estimate those, both sort of in if you don't care about privacy and if you do care about privacy. Okay, notation the same as before. Let me just sort of, for those of you who, as we didn't remember when we started this paper, what a sigma finite measure space is. So you have some measure space, think of R, okay? And it's sigma finite if you can decompose it into countably many pieces which all have finite measure. So in R it would be the interval 0, 1, 1, 2, and so on, or any other way you want to divide the intervals into sort of finite pieces which have finite measure. And the Lebesgue measure will be denoted by lambda. Okay, so dense models, okay? So the probably oldest dense model for graphs is sort of the stochastic block model, introduced by, I don't know whether I should call these social scientists or statisticians, maybe a mixture. Statisticians. But they were sort of motivated by sort of studying little social networks. So you have sort of, you have k possible groups, boys and girls in a high school. You have some probability, sort of maybe it's 55 to 45, the percentage of boys to girls, so everybody gets born with some probability of being a boy or girl, or more general in one of the k groups, and then your connection just depends on the groups you're in. And so that's one of the oldest model, and there's sort of, I don't know, probably thousands of papers on the stochastic block model in the statistics literature. A little younger, well, actually, maybe even older, are Graphon models. They were not known under this name until we actually invented this name in this paper. They had sort of a different name for a while. Let me give you the model first and then tell you a little how the history relates. So the model is, in the dense setting, very simple. Jennifer described it. You have sort of a feature which describes every person. I get a feature from a random distribution, and it has to do with sort of how much I like classical music versus jazz. It's my intelligence, my height. And then the probability that I will connect to Susan, well, she has her own feature vector, which was chosen at random by God or whoever, here just by a coin. And then the two of us connect with the probability, which depends, for example, if I like more classical music and she likes loud rock music, then maybe we're not so likely to connect. And originally, so these guys did not really introduce it sort of implicit in there, I will tell you in a moment. The first place where it appears explicitly is in Hoff, Rafferty, and Hancock, which were called latent position models. And what they did is this feature space was a metric space, and they wanted to study whether you have homophily or the opposite. And so they were choosing W as a function of the distance in the feature space, and they wanted to know, are you more connected if you're nearer or farther in the feature space? So they wanted to see whether this was an increasing or decreasing function of the distance. But once you are that general, it's very easy to say, well, it doesn't have to be a function of the distance, can just be a function of the two features. Okay, so maybe here you would call it a latent feature model. So that's them. Lovász and Szigeti invented it as a limit of a sequence of graphs. So we had worked together with László on sort of formulating this notion when sequences converge, what should be equivalent, but we hadn't come up with a sort of compact limit object. With Lovász and Szigeti, they introduced Graphons over 0, 1 at these. And then actually, just like Jennifer had this error in the other way back, invented this random graph models to construct the error back, that for every graphon there is a sequence which converges to it. Bolasbas and Riordan really created this model to generalize random graphs and studied the phase transition as you sort of have average degree about 1 in this, and when you have a giant component and not. We invented the name. And actually, Aldous and Hoover showed that they studied exchangeable models. And I will tell you actually in a moment that they actually proved that they are described by a random graphon. But they didn't know that it should be called a graphon. OK. Then you may ask the following question. Do actually, in this general setting, you generate now a large graph, does it converge to this function? Well, what does that mean? Okay, so this is a sequence of graphs, some adjacency matrix. And now I have a function over some feature space, okay? I mean, maybe the feature space is the sphere in 5 dimensions, okay? How should I compare a graph on 20 nodes to a sphere in 5 dimensions? Okay, so now recall that if both of them live on the same space, then it's very simple, because then we can just say, okay, I take two measurable sets, and I do exactly what we did for graphs of the unit interval. We look at the cuts. Here you have an example where S is the complement of T. As Jennifer said before, you can sort of put general S and T, or you can choose S intersected T empty. They all differ by some constant factor. So this one is nice because it's sort of bilinear. You don't have to really, once you have S, you don't have to worry about T. So there's advantages of all of them. I choose this one. But what if they are on different omega, right? If these two measure spaces happen to be isometric, so if I could find a measure-preserving transformation from one back to the other, then maybe I could just say, well, I apply this measure-transferring transformation to the arguments of my function W, and now I can compare these two. But in this general setting, I mean, for example, maybe actually W is a block model with 2 blocks, and Gn is a graph with 5 vertices. There is no measure-preserving transformation between the two of them. Okay. So what do you do? Well, if you're a probabilist, you sort of think for a while and you say, well, I remember there's something called a coupling you can use in this case, so that's what we do. Okay, so you take...
I want to mention that there's a mistake in the literature.
No, wait, it comes. So we define the distance now by saying the following. We take sort of a so-called coupling, so we go from one is the space, it's the other, to the product space, and we now choose a measure such that the two marginals are mu1 and mu2. And now, since we now both of these guys live on the product space, we can take the difference and calculate this cut norm, and then we take the best coupling you could imagine. So this is sort of the best if the two of them were two graphs, okay, if they have the same number of nodes, I could just try to minimize over alignments by relabeling of vertices. If I allow for this coupling, that's the same as allowing fractional mapping of vertices. I can map 1/3 of this vertex and 1/4 of this vertex together. So this is sort of like fractional permutations, if you sort of don't know what couplings are. And so now it turns out that if you do that, then actually you get convergence. Okay, so Lovas and Zaghetti proved that for the interval 0, 1, and actually not in this cut norm, but for the so-called left convergence, for convergent subgraph frequencies. We then proved it in the cut metric, and then here it's proven for, this is a paper with, so most B's will be me. Maybe then there could be, B could be Bolabas, or it could be Bickel. I don't think any other B appears. Most C's will be Jennifer, Chase. It could be Cohn, or it could be Patrick's co-author, Choi.
David Choi.
Okay, and I will not go through the rest of the letters of the alphabet. Anyhow, so, and L will be Lovas. Typically, in this talk, the older one. So, anyhow, so in more and more generality, this theorem was sort of proven. So actually, this is true. Okay?
Still, it's more or less the same question that I asked earlier to Jennifer. W is a function.
Yes.
G and W is a random function.
Yes.
So
what this probability one.
Okay, thank you. Yeah, good, thank you.
Okay, so good. And it's sort of, I mean, okay, this probability one. So now comes the following question. Okay, so we get convergence. The question is, so this sort of seems to almost already give me estimation, right? This seems to give some way of consistency, right? Because it says, well, Gn of W essentially describes W, right? It's near to it in the limit. It's a very weak notion of consistency because the cut norm is a weak notion of convergence, and it also leaves out a question which is that of identifiability. So let's get to that first. So given this sequence, can we uniquely identify W? Okay, and the answer is clearly no, because if I take another W which differs from this by a measure preserving transformation, so W phi is W phi of x and y is just W of phi of x and phi of y. Okay, and if W is measure preserving, then this thing has the same distribution as this thing. So therefore, the graph on the W prime will lead to exactly the same random model as the W model, because I've just relabeled my features, right? Maybe phi is the rotation on the features, so it's just, yeah?
Does the optimal mu in the coupling, does that exist? And if it does, is it informative or interesting?
That depends on the space you're working on. So if you're working on an atomless Borel space, it does exist. And it is actually related to this thing, because then you can, well, okay, so if you have a coupling, obviously, then you would have that, well, okay, I have to first go, okay, I will tell you in a moment. So now you might ask, is this actually if and only if? And some famous statisticians who will be unnamed actually claimed that in their paper, so you have to sort of, so the paper is morally correct. It's one of the first papers on introducing.
It's a PNAS article, actually.
Yes, and it's one of the first papers to talk about non-parametric Graphon estimation and things like that. And it's still a very influential paper, but they got a little detail incorrect, namely, they thought that this is everything you can do. And it turns out that even if I have two Graphons over the unit interval, this is not enough. What you need is actually, you need two such maps. In general, you can sort of, so they have the same distribution if the cut distance is 0. which comes to your question about the coupling. I will go to that in a moment, which turns out to be the same, that there exists a third graphon and measure preserving match that this is the pullback of Z and this prime is the pullback of Z. If the underlying space is 0, 1, or more general an atomic Borel space, then in this definition of the cut distance, the coupling is actually attained. And if I denote by, I wrote sort of W1 minus W2 cut norm, but I cheated because I should really have written here, because I have to write here the projection onto the first coordinate, here's a projection onto the second coordinate, and now this is phi 1, pi 2. So if this is now 0, right, then we have that W1 phi 1 equals W2 phi 2, and that is actually was known to Hoover, for example, and then was forgotten in the literature. Sort of some of the younger statisticians, not that much younger, forgot it and sort of made this mistake of not realizing you need two of them. And in the general setting, you actually don't get a coupling here and you need this third graphon. Okay? So Diaconis and Janssen pointed out, had this relationship. They sort of, it's more or less, you can find it in, and you can find it in these papers as well. And then they pointed out that if you go to Hoover's paper, you can sort of do this version here, and we then, in together with Lazzi, had this general version. Okay, so we call them equivalent in this case, and it turns out that any graphon is actually equivalent to a graphon over 0, 1. If you know the Aldous-Hoover theorem, I can, well, I shouldn't wait and spend that. So you can deduce it from the Aldous-Hoover theorem, actually, which these two guys pointed out. This may in practice be a red herring, because even though you can find sort of these measure-preserving transformations, maybe your original graphon is a very nice graphon on R5. Okay, it's bilinear, it may be super nice. Well, measure-preserving transformations tend to be ugly. And so then your graphon will not be Lipschitz continuous and anything anymore. So actually, if you want to do any reasonable estimation, it might be a really bad idea to estimate over here rather than over the space where you really live. But for many mathematical proofs, this is very convenient. And a lot of the literature actually just deals with this case because it's sort of easier. But okay, good. So I will do half an hour for the review of the dents here. I should speed up. Okay, so a sequence of random variables is called exchangeable, an infinite sequence, if the joint distribution is invariant under permutation. And the famous De Finetti theorem says that if you have an infinite binary sequence which is it's exchangeable if and only if you can find a probability measure on 0, 1 such that your sequence is generated as follows. You first choose a random bias for your coin, and then you choose your coin's IID according to this random bias. And what this P is, well, almost surely it's just the limit of the density of the coin, of the heads. Okay? And that raises the question whether the same holds for exchangeable arrays in 2 dimensions, and that's the famous Aldous-Hoover theorem, which, I mean, people first thought maybe it's just also 1 or 2 coin flips. It's much more complicated, so let me give it to you here, but I give it to you in a slightly different form. So a sequence is projective if you can get the distribution on n-1 vertices from that by just looking at the induced subgraphs. Okay, and if you can do that, you can couple them in such a way that it holds this probability 1. And it's called exchangeable if for all n the distribution of Gn is invariant under relabeling of the vertices. Okay? It's easy to see that these sequences are projective and exchangeable. And Aldous-Hoover says it's an if and only if, except for a random choice. So if Gn is projective and exchangeable, then there exists a probability distribution over equivalence classes of graphons, such that we can generate these guys by first choosing a graphon, or if you want, an equivalence von graphon, or an element. So you choose an equivalent class according to mu, then you choose some representative from your equivalence class, and then you set the graph to this inhomogeneous random graph. And furthermore, Gn converges to W in the cut metric.
They didn't have the,
They didn't have.
So-
they didn't have the cut.
That
So,
was,
wait,
that was
can I?
our addition to that.
Guys, yes, I'm quite aware of that. So this theorem should really get a few additional names, because it's only now that we know the theory of graph convergence that we can write it in this nice form. But I want to write it like that because this is the analog to saying the density of the coin flips is the P.
So we-
And
Yes.
so actually the person who first realized it was not us, but it was your sort of beloved husband together with Svante.
Right.
He realized that our papers actually allowed to realize the dream which originally, so Aldous actually wanted to do something like that, but he didn't know when two graphons are equivalent. And therefore he couldn't really formalize, I mean, the idea of a measure over equivalence classes of graphons was something they couldn't formalize. The mass was not there, okay? So this piece,
But David Aldous did remark in the paper that he wanted the analog of convergent.
sure. Now, Hoover actually did know these equivalence classes, but he still didn't have a metric to sort of formulate this. So we really need this. So the way, how did they get around of it? They got around it by saying, so they had a distribution over just an auxiliary random variable, let's say between 0 and 1 uniform. And then instead of a graphon on 0, 1 to the power 2, they had 1 to the power 3, and then used the auxiliary variable to actually generate this random object. And that way they didn't have to come up with the sigma algebra on the set of graphons, because otherwise we don't know what it means to be a random graphon. So they didn't have really the concept to formalize it. But this was first observed by Svante Janssen and Percy Diaconis. Okay, good. So now we want sparse graphs. So there is and there's a few things we would like. Okay, so in real life, graphs tend to be sparse, and they often have power law degree distribution, so we would like both. So sparse seems pretty easy. We just can do, for example, G and P is sparse, right? If you send just the density to 0 as n goes to infinity, it's a sparse graph. It doesn't have much of a power law. You can choose the stochastic block model and just multiply this connection probability by some rho n and send rho n to 0. So both of these you could get from the dense model by subsampling. You first sample a dense graph, and then you just only keep each edge with probability rho n that's equivalent. Okay? So you can do that for a general graphon model, and actually Bolabas and Riordan already did that in 2007. So you just connect vertices which feature xi and xj with probability rho n times this w. And you get, or equivalently, you first do the dense one, and then you subsample it with probability rho n. So this is very nice. It gives sparse graphs, but unfortunately no power laws. Indeed, if you do sort of a little bit of calculations here, you all know it from the random graph, the maximum degree and the average degree differ by at most a log. And as soon as the density grows at least like log n over n, they're of the same order. And if that grows faster, actually their ratio converges to 1. So this does not give you power laws. On the other hand, we have sort of some idea from the theory of graph limits how power laws should look. They should correspond to functions which have power laws. So there are two ways we can make functions have power laws. We can allow ourselves to go into the positive real values there, then we can do something like this. Okay, and now this thing is sort of larger than 1 always, so we better multiply it by some density rho n, and it still is sometimes larger than 1, so we take this minimum and then do that. Jennifer already described it to you, and that actually will give you a graph with power law degree distribution. If you choose alpha 1/2, this is how it looks. Another way you could do that, you say, well, let's keep the 0, 1 here, but let's spread out the variables. So then I can choose w of x and y. I just add here 1 because I say I want it to lie in 0, 1. Okay, so no singularity at 0 anymore, no singularity at all, but this thing just decays very slowly at infinity. And now you can't do a uniform distribution over R plus, so what do? We do a Poisson process. Okay, so we have a Poisson process whose density grows with time, and then we connect again I and j with this probability. So I will write down this formally, and if you do that, this is how it looks. So what happens is that you get here some pretty dense core where the thing looks really like a dense graph. The degrees are proportional to n, and you get down to vertices here which have degrees of order 1. So it's actually, whereas in this setting, both the max degree and the average degree will be of order rho n, but if you divide the max degree by the average degree, it will be a power law. So this is sort of, again, this model is sort of Bolabas and Riordan did. They already looked at this general W. They didn't do much with it, but they defined the model, and we call it an inhomogeneous random graph at target density rho n. Okay? And so it generalizes, obviously, Erdős-Renyi, which are the minutes. And it gives power law degree distribution. I already showed it to you. It converges to W in the cut metric if rho n goes to 0 and the density, the average degree diverges. Jennifer talked about so Jennifer indicated the proof. She talked about the average divergence of the degree. This one is sort of not needed, except that it will still converge, but not to W, because obviously if rho n doesn't go to 0, then I will always cut off something of W. So let's say rho n is 1, well then this converges, but it doesn't converge to W, it converges to the minimum of 1 at W. So, but as soon as the density goes to 0, sort of the piece you cut off gets less and less and less, and it converges. And it's exchangeable, but it's not projective, because if you go from Gn to Gn, if you go from Gn minus 1 to Gn, you have to delete some edges. Or in other words, if you want to, so this is a typo. So if you want to go from here, yes, it is a typo. If you go from Gn minus 1 to Gn, the density goes down, so you have to delete edges. Or in other words, if you want to go from Gn to Gn minus 1, you have to reinvent some of the edges. And that's not projective. Okay, there's a typo here. So now, the other one, okay, so the people who first came up with that were Caron and Fox. And we, together with Nina Holden, generalized it, and there's another generalization I will give you in a moment. So in general, we have some arbitrary sigma finite feature space. Again, think of sort of gender but now maybe income is unbounded. Okay, so we don't, and maybe there's no probability distribution on income. Maybe it's uniform. It's not quite believable, but anyhow. And so now assume you have an integrable graphon. Okay, and so in their example, they sort of said, okay, I have some affinity of nodes. Okay, so how much I want to connect to somebody else. I described it just by some real number, and they said I put Lebesgue measure on it, but you have this integrable graphon. Okay, and now we take a Poisson process of density T times your original intensity, and then we connect two vertices with the probability depending on the two feature vectors. Now, unless this guy has finite measure, you will have infinitely many vertices in your Poisson process. But since W is integrable, you have only finitely many edges, so if you leave out all the isolated vertices, you get a finite graph. And that's the graph we want to look at. So you can think of it as follows. Maybe I'm a new social network. I have this really lot of people I could connect to. I think of them as infinite, okay? So there's this infinitely many people, but they have different probabilities of actually connecting to each other. So in the beginning, I will only see those for which the features are such that this W is really large, okay? Because in the beginning, it's very sparse, and I only pick out the few. And as sort of time goes on, I get more and more vertices with lower and lower affinity. So in this model, the early vertices tend to be those which actually had higher affinity. So here is a picture, okay? So here's some time. You see a piece of the real line. 4 vertices have shown up here. And if you do this process, these have connected, okay? Observe that there's one of them, the first vertex here is invisible because it hasn't yet connected to anybody. And as time goes on, there are new vertices coming. This vertex 1 gets more and more chances to connect on somebody, even though he's pretty shy. There comes somebody like Jennifer marrying a shy guy like me, and suddenly I'm married too. Okay, so this vertex 1 finally gets sort of...
Other people can marry you this time now.
That is true. Now it's sort of... Actually, in this thing, I will have infinitely many wives as the life goes on. Because once you connect to one vertex, you will connect forever. Anyhow. So this is sort of...
I can have infinitely many husbands too, but let's go.
That's true. You will actually, with probability 1, have infinitely many husbands.
Starting to sound like couples therapy.
Yeah. So, okay, so the first time a vertex appears is its birth time, but we consider it hidden until it actually appears. Okay, so we can formulate an edge process by labeling each vertex by its birth time and define a random measure on R+ by putting atoms of unit mass at the 2 endpoints. Well, I mean, that's a cross of the 2 endpoints. And then we have we can take an infinite graph by taking the union over all of these. Okay, and now, so here we go. Here's our Poisson process. Here are the vertices which have some labels. They also have labels by the features which I haven't even drawn. You forget all these labels and just put the times, and you get the edge process. Okay, and now there's something you will observe. If you do that like this, for this process, you started off with actually a Poisson process on your original space, cross R, and the process had density lambda, Lebesgue measure, cross your measure, whatever it was. Well, in the direction of time, this measure is invariant under measure-preserving transformations. Right? Because it's a Lebesgue measure, you can sort of move things around. So, and now if you integrate out the features, you're only left with the thing in time. So therefore, this process will be invariant if you apply the same measure-preserving transformation here and here. So in other words, this process is exchangeable as a continuum process. Okay, so this is the analog of, so for an infinite matrix, you just do finite permutations of the vertices. For a process here, the analog of permutations become measure-preserving transformations, and this measure in the square, which is an analog of sort of an infinite array, will be invariant under this transformation. It's exchangeable. Okay, so, but let me first sort of mark that if you look at the stretched objects Jennifer looked at, it converges in the cut metric. It turns out to have, therefore it has uniform regular tails. Jennifer proved to you, while she had less mentioned, that if it converges, it must have regular tails, which means in this setting that I can just, you can vary, so you have this sequence of graph, you get this sequence of stretched graphons, but most of the mass stays sort of in a finite region. That is what it means, it has regular tails. So it's not that this graph gets more and more spread out as time goes on. It sort of keeps its mass essentially in the same region where W had its mass. It inherits sort of this regularity from W. It gives power law degree distribution with very long tails. Okay, here are the two examples. Okay, and the edge process is invariant under joint measure preserving transformation of both coordinates. And so now we prove the analog of the Alvus-Hüller theorem. So if you have a projective family with uniformly regular tails, and you define the edge process, so if it's projective, then you can talk of union because the previous one looked like the later ones. And so you can formulate this infinite process, okay? And now this process is jointly exchangeable if and only if there exists a measure mu on equivalent classes of Graphons such that GT can be obtained by first choosing this random W and then generating the process the way I described it. And furthermore, you get convergence in the cut metric. So this is again the theorem with De Finetti proved and Aldous and Hoover dreamt of. We also dreamt of, but then we had this really strong student, Nina, who proved it. And so now I should mention, essentially, I mean, in parallel to us, we sort of we each discovered that the other group was doing almost the same. So Roy and Weitsch were doing something very similar. Theirs appeared a few months before ours, or a few weeks. And they have a slightly more general setting. That's why I explain this later. So they have an object they call a graph-X, which consists of a graphon. But in addition, you have some function which just depends on one variable, and you have just a single density. And now you have the Poisson process as before. You add edges as before. But now you do something in addition. Each point, so they have some chance to connect to each other, but they also can grow sort of leaves of a star at this rate. And finally, you independently can add isolated edges at rate t squared times lambda. And now if you look at this guy, it will be exchangeable again. And there's actually a theorem by Kallenberg you can use to prove this theorem, which says that if you have a projective family which is now locally finite, so we had here regular tails, then you actually get this more general object.
What are isolated edges?
Did I say isolated edges? Oh, they're just... So I have here my vertices. There's a...
You add new points?
Yes, you add just...
You like two new points with an edge between them?
So just add... So it's essentially just a random point anywhere you want here. Think of it, you have sort of...
Points, or edges from this point I.
From this to this. Okay, so I just randomly choose a point with the Poisson process in the plane and just put it independently. Okay, and then the other one is sort of depends on the features. So if this guy, maybe W of that feature is 0, in which case it stays sort of, it will never connect to anybody. Okay, just stays hidden. But maybe it doesn't stay hidden because it collects a star, so then you see it. So almost you can think of it, okay, here's R plus and R plus, which comes from the features. And here is sort of some additional stuff. Namely, you can sort of have, and this you should also think of R plus and R plus. So you can put just points here at random. This is the independent edges. Here you connect them according to their feature values. And here you grow sort of, depending on the feature value, you grow sort of a star around them, this rate which depends on this function. Okay, so this is the most general, and Kallenberg actually has a slightly more general theorem which describes an arbitrary exchangeable random measure on here, which is not necessarily a point process, and therefore there are a few more terms in the Kallenberg theorem. Both Victor and, what's his first name? Dan. Both Victor and Dan and we rely on the Kallenberg theorem to prove that if you assume it's locally finite, you get some conditions on W, and S has to be integrable, and well, lambda is just a positive number. And if you assume instead that it's locally finite, that you assume just regular tails, then you can rule out that you have the stars and the independent edges. Okay, so now I have 15 minutes to talk about Okay, yeah?
I just ask a quick question.
Yeah.
Can you remind me what this edge process is? Did you?
So,
Is that related to the thing in the R squared, or
that is related to this guy in this thing.
to the points in there?
Yeah.
So then that's my question. You have a sequence of graphs,
Yes.
and then you say the associated edge process. How do you associate? How do you make that association? Because these are graphs versus points in space.
Well, you see, I have written here t squared lambda. So let's first describe this point process only up to. So let me make it precise. So here we have a time t up to which I'm looking for the moment we'll take the limit t, or the union over t, all t in a moment, right? So at time t, I do the following. I choose a Poisson process at intensity t times your base measure. Okay? So think of some other direction here, right? And I have sort of a Poisson process where this is sort of the direction of your feature, so you get sort of all these points with features here. Okay, and they appear at sort of random times, which is sort of, there is more and more as time goes on. So if you can think of them as points here, where this is the time it appears and this is the feature it appears. Now I put the time here, and now I look at two of them, and if the w of x I y is sort of gives me some probability, I flip the coin, and if they get connected, this other guy here will have its own time, and I put a point here. Okay, that comes from w. In addition, I forget w, I look at this Poisson process, and for each of these points I grow a star of this feature process, right? So in other words, well, at the time this guy, so one of the coordinates is the time this vertex was born, and the other coordinate is a time which goes on as you grow more and more vertices in this star. So that is a second point I put here, right? This comes sort of from, and there will be more and more over this one point because that corresponds to the star I'm growing above this point. And finally, I just randomly throw down some points here from the Poisson process, which I just have on the positive quadrant. And if I only look up time t, then you just see t squared many. Have I described?
These extra pieces may make it not have uniform tails.
Right, it will not make it have uniform tails.
Right, it will make it not have uniform.
But that was not. Is the process
that's
clear?
good. Then my question is, with the exchangeability condition is on the point process.
Yes. Right, and the exchangeability is clearly again. This piece is exchangeable because the point process. This is sort of the simplest random measure you could exchangeable random measure on the positive quadrant you could think of. Just put a Poisson process with constant density there, right?
But right, it's on the point process, so it has to do with transforming space, not permuting labels in a graph.
Right. No, so the exchangeability is exchangeable of the time label, right? So if I think of t as time, then that means that in this whole process, the labels in time don't really matter. If you do a permutation of the time labels, the process is invariant. It's obviously true for this stupid thing where I just sort of put points sort of at density 1 into the infinite quadrant. Clearly, if I move things around, it's the same thing here and here. This is invariant under joint exchange, under many. This one has the largest class of invariances, right? And so now observe, I have written here random in quotation marks because when they wrote this paper, they didn't have yet answered the question of identifiability, and they had not yet a notion of convergence. So they couldn't state it in the sort of nicer form. And we have been working we needed 2 students for that. So with Victor, we have come up with a notion of convergence which works in that setting. And with Lazzi, we have
Young lot.
with young Lazzi, we have worked out the identifiability question. And if you put these together, you can write the theorem in the nice form of definite. Okay, so I have 10 minutes to estimate all these graphs.
Notice that the time divergence between the two clocks. You can pick the clocks you prefer.
Oh, I see. Okay, I have 12 minutes. Fine. Okay, so what do we want? I will only do that for the first model. We are working with Nina on doing it on the second model. So you have this inhomogeneous random graph, and you would want to consistently estimate this graphon. Okay, say in the L2 distance. Now, given that W can only be identified up to equivalences under the cut metric, how do we even define consistency? And there, two of our co-organizers here came up with a very nice notion. They said, well, what you should estimate is actually equivalence classes under the cut metric and not W itself. So in other words, you should use an invariant version of the L2 distance to define consistency. And that's what you should do, okay? So we define an invariant version of the L2 distance just the same way as before. We use couplings. I should put the projections here, which I didn't. And then you just take the L2 distance. Okay, and if you use this distance, and then consistence just means that your estimator W hat should go to W with probability 1, both to if your algorithm has randomness and with respect to the sample as the number of vertices goes to infinity. Okay? So what we will show is that the simplest algorithm you could think of, namely the least square algorithm, works. Okay? So what do we do? I have to define a little bit. So what do we have here? Well, so this will be the least square estimator, okay? But let me sort of go through that slowly. This is the adjacency matrix, okay? Here I have some k by k matrix, but then I want to spread it out to be an n by n matrix. So this B pi is actually a block matrix. It's a matrix where a lot of the entries are the same, and it's sort of, if you permute it around, then it just consists of k blocks where each block consists of adjacent labels, but there's no reason the labels should be adjacent. So because you have these models which are exchangeable, so you just, depending on the draw of your coin, you get some permutation. You have no idea which one. So therefore, you minimize over all these permutations here. And then you want the argmin of this guy, okay? And you want sort of essentially equal, you can do different from equipartitions, okay? So all classes having the same size, or if it's not divisible, plus minus 1, or you don't have to do all size. You can say the smallest class has at least some size. So there are various versions. This is the simplest to write down. Okay, and now, given an instant of your inhomogeneous random graph, you output the k pi k block model, which is the argmin of that. Okay, and then our theorem says that, very natural, since we are doing an L2 estimation, it will work if W is an L2. I normalize it such that this is 1 just for the reason that then the density of the graph is actually rho n, otherwise the density of graph would be rho n times the integral of W, so this is just for notational convenience. So if rho n goes to 0 and the average degree diverges, and you send the number of blocks to infinity slow enough, then this actually works. Okay, and I have a sketch of the proof, which I will not give you. So related work, maybe I should talk about it a little bit. So for stochastic block model, it's sort of ancient. People have started to estimate those. I think this was Monte Carlo, but maybe the experts under you know better than me what it was. This is the first reference I don't think they had proofs, but it was the first place where people actually were estimating the stochastic block models. And by now we know how to do that pretty optimal in the dense, but actually in the general setting. So these guys give an algorithm, and they give matching min-max lower bounds. These guys prove that there is sort of a phase transition at the density where you can do it, and after which you cannot do it. Below it, information theoretically you can't do it. Above you can do it. And for dense graphs and general graphons, Kallenberg actually sort of didn't formulate it as estimation, but if you want to look at it, there's some very inefficient algorithm to actually estimate W in there somewhere, I'm told. I don't know, have you actually found where it exactly is in there?
Yes,
You
like theorem 3.
Okay, so it really is in there.
But he calls it estimation.
Oh, he calls it estimation. And it sort of is similar to estimating subgraph frequencies, which turns out a very inefficient way to do this. And then sort of Choi and Wolfe came up with sort of I think they did already least squares. These guys prove the matching min-max bounds, and Chatterjee does some spectral stuff where you sort of cut off the higher frequencies and output that as an estimating graphon. For Sparse and Hölder continuous, that's the paper Jennifer mentioned, we were really motivated by. They introduced the notion of looking at the equivalence classes. Many of the other people went around the identifiability issue by never estimating the graphon, but outputting just the matrix W of xi, xj. Because if you go into that, then sort of the problem doesn't arise. And okay, so these guys again have min-max bound, and the least square algorithm was sort of first analyzed by Chow and Wolfe and this group, where are we? Gao et al., where they have min-max bound. And then in the Sparse case, we did that with Adam in the same paper. We did the private one, and these guys prove min-max bounds. Okay? So our contribution in this paper is that we do it on general probability spaces, and we can allow for unbounded W. So everybody else before was bounded W. So we only need L2. So this at least allows some power law graphs. I will not do the proof for you. I want to mention though one thing. Okay, so what it gives is when you look at, so this will be the end result. Okay, so you prove that you output this sparse matrix, you divide it by the density of your graph, you get an estimator, which is actually, what is this thing? That's the best estimator you could have, right? Because here I look over all block models in L2. So that's the best block model approximation L2. So in this sense, this is an oracle inequality. We show that up to an error which goes to 0, you actually get the best, or it's not even by a constant, it's just constant 1. You get, yeah? Did you raise your hand? No? And then it's easy to see that the oracle thing goes to 0 if you send the number of blocks to infinity. So if you do that slow enough, then it sort of follows that you get this. And actually slow enough is this. Okay, if you have additional information, you can write down sort of some powers. I will not go into that. Okay. Privacy. So in general, assume we have some database information about individuals. Me, Jennifer, Clinton, and so on. Trump. Okay. Can we release statistical information about this database while respecting the privacy of the individuals? Okay, can you do that? And it's relevant and even more difficult for graphs because others, via their connections, reveal information about us. And this is not only mathematical theory, but for example, people have done that on Facebook, and you can actually, just from the links on Facebook, can have an idea about the sexual orientation of people. I think in this setting they actually knew the sexual orientation of some subset and inferred the rest. but even if you didn't know that there are sort of, well, if you assume there are only 2 or 3 classes of sexual orientation and you look at your large graph, and then you sort of see, okay, there's one orientation which is there's a majority that will be heterosexual and so on. So you can, even if I don't tell you the labels, you can actually infer them. So if I just give you the graph, I can tell you the sexual orientation of the vertices in that graph, because you just cluster it and it becomes obvious. And therefore the naive anonymization actually doesn't help, because it's just you cluster the graph, you see it again. And I mean, this is well known with social security numbers and things like that. I mean, giving people numbers is just not a good way of privacy. Even though, I mean, medical record, everybody does this, okay, but it's just actually a really bad way. That's why whenever you do research with medical data, you have to sign that you are aware that you could de-identify, but you promise not to do it. And there should be stronger laws that if you actually do it, they throw you in jail. I think there are no laws about that, but anyhow. But we would like something where we don't have to rely on just having good players, right? So that is sort of the notion of differential privacy. So what is that? So we have some algorithm. It happens to be, if it were not random, you can't do it. So you have a randomized algorithm. It's called node private. If for 2 graphs which differ in at most 1 node, and any event. So what is an event? An event is a possible answer or set of answers to any question you might ask, okay? So this algorithm gives answers to questions, and no matter what you look at, if you look at the probability that the answers are the same between the graph I'm in and the graph where I have been removed should be very near to 1. Okay, so that's the notion of differential privacy introduced by Cynthia Dwork, Adam Smith, and
Emery, a couple of others.
no, one other. Anyhow, so some precursors. Anyhow, so previous work did that mostly for individual graph statistics and dense graphs, and we will want to use what's called the exponential algorithm. So instead of minimizing this L2 distance, we sort of take a distribution over that. And epsilon is this privacy parameter. Delta has been chosen in such a way that if I change Gn just by 1 node, this object doesn't change by more than delta. If that were the case, then this factor is sort of only changes by e to the minus epsilon over 2. Then if you calculate the normalization constant, that gives you e to the minus epsilon, and that is this. Okay, so it's clear that what you have to do, you have to choose delta depending on how sensitive this object is to changes in the graph. And then the question arises, well, but maybe for that I have to make delta really large. Then this thing doesn't depend much on the graph at all, and therefore instead of outputting the least square estimator, I put out just a random b, and you can't prove consistency. Because that's exactly the question, can you do that? And the answer is yes, you can do it. Okay, so if the graphon is bounded, and if your average degree grows at least like log n, then we can do it. Okay, so then you can modify this algorithm. Actually, the way it's written there, it absolutely doesn't work, but you have tweak it and tweak it and tweak it. That's why it's a paper. And so it is epsilon. So what can we do? It's absolute private on all input graphs. And if the graph was generated from this model, it's consistent. So in other words, it's worst case private, right? Because so assume I'm at Facebook, and you say, I have this differentially private algorithm, and if this graph was really generated from this exchange model, then I promise it's private. But if it happens not to be generated from that, sorry, it's not private. Then I'm going to say, come on, you and I both know that it's not really generated from that model, so you have no guarantee, just forget it. So you want the guarantee independent of the model. Okay, so that's what this is. The guarantee is independent of the model, And then, but if the graph was generated from this model, you estimate the model correctly. Okay, and I will stop here.
Tea outside. Let's take a few questions before.
So in addition to estimating the graphon, maybe sometimes you'd also like to estimate some embedding of the nodes into the feature space omega?
Very nice question. So it turns out that if you assume nothing more than what I've written here, then there's this identifiability issue. You can only, so you can't do it. Now, if you assume that, let's say we knew that the graphon has to, okay, if the graphon were continuous, okay, then suddenly you can't just go from 0, 1 to the sphere in 5 dimensions, because that's not a continuous transformation. And you need a little bit more conditions, so it has to be sort of nice. So if it's nice, it shouldn't have twins. In other words, the W of X and Y shouldn't have two identical rows. That's essentially the two conditions. The rest are sort of not so interesting conditions. If you have the two, then it's actually known that the topology of the graphon is determined in the limit. That doesn't give you yet estimation, because it doesn't tell you that from a finite sample you can consistently estimate. It tells you if you have the whole infinite sequence, you can actually estimate the underlying topology. For example, you could estimate, well, what's the dimension of the underlying feature space. Now we are working with Lazzi,
Young
Lazzi, on actually showing that you can do what you really want to do. If you have a large enough sample, you get an estimate for the topology, and that estimate is asymptotically consistent. For example, what we can do, we can estimate the dimension. Now, and we use, have you heard of persistent homology?
Yes.
So persistent homology is this idea I have data, okay, and the data are supposed to come from some manifold embedded in some high dimension. But what you see is sort of just data, right? And now what you do is when you want to estimate this manifold, you coarse grain on different scales. And if coarse graining on different scales leads to the same manifold, you claim that's the underlying manifold. I know you're shaking your head because I'm making it much too simple.
No, but it never works. Persistent homology doesn't work because it presupposes that you have the uniform distribution, which you never have.
Okay, well, we show that you don't need uniform distribution in this setting. So you have some problems here which are obvious, right? If this thing, it could be a line in high dimensions, or it could be a thin sausage. So obviously, if your noise is large enough, you might not be able to distinguish the sources from the... So you can only say, well, for example, we will output the dimension is this, but in the other direction, maybe it could be thick and have a very different dimension. So you have sort of some approximate dimension, but you can actually show that that sort of in the limit works. Okay, so it's consistent. Now you may say in practice it will not work, but we actually don't make any assumption on the distribution. I mean,
well, the persistent homology, the method does make the way it works, they make radii, and they're all the same radii, regardless of the density, and it only works if you have uniform distribution on the manifold. It doesn't work any other way.
Right, so there's actually interesting questions coming here. Anyhow, so we prove that you get sort of an estimate for the dimension which is sort of asymptotically consistent.
So you should have this notion of graphon and so on and so forth, but what about properties that are not captured by a graphon? You need to invent a new notion of convergence for a property that's not captured by them? Or?
Well, so there are sort of things, for example, you can make the graphon, instead of to have just values in 0, 1, you could have labels, okay, which will be important, for example, if I want to do recommendations, right? I don't have just edges, but I have sort of 1 up to 5 stars. But you can actually generalize the theory to I mean, in the simplest case, you could just think of it as if I have 5 possible ratings at 5 graphs on top of each other. They obviously have some relationship, so it's not quite as simple. So we're actually working with one of the graduate students on sort of doing...
So Christina Lee and Deborah Ratcha, they had generalized or weakened the conditions on the Chatterjee work, and we are further weakening them to the case of Sparse.
So that you can do sort of movie recommendations or things like that, where you have sort of, you put an edge if somebody rated a movie, but then there's also the rating, and it's a slightly different objective. You are not necessarily interested in estimating the graphon. You want to fill the entries of a matrix you haven't seen, assume, but under the assumption that the underlying model is one of these forms.
So it's an alternative to like a low rank approximation to the matrix that actually gets you much further in this particular case.
Another
Sparse recommendations where, you know, me and somebody else in the world probably have not seen too many common movies.
So, and another direction is the one Jennifer mentioned with A/B tests, where you sort of want to see, well, how much extra money do I make if I'm a search engine and I give my advertisers a lower reserve price. Then it's cheaper for them, so they might invest more with me. And maybe I make more money because they invest so much more that the lower reserve price makes up for it. And then you want to test that in an A/B test. And then this is one of these examples where if I give Susan sort of a discount, but I don't give Jennifer one, then she will invest much more because things are really cheap for her, because Jennifer can't compete. She doesn't get a discount, but you get a discount. So I'm saying, oh, happy giving discounts to people will get much more people into my system. So now I give everybody a discount, and suddenly it doesn't work anymore. Well, that's how standard A/B testing is done today. Okay, so, but you can correct for the network if you have some model how I, on top of the graph, say that I have some spread of how sort of we spread well. So you have some linear model of the economics, you estimate the parameters of your linear model. You actually don't have to do that. You estimate in the end sort of the network effects correctly to have an estimate from doing just a partial treatment to estimate what the effect on the whole graph would be. I agree there are some other models, for example, the bounded degree models, the Benjamini-Schramm model. It's not described by a graphon, right? So there may be models which are exponential random graphs are not described by a graphon. I'm not saying it's the only model, but it's a class of model. If it's sort of, there's some situations if you have
We have theorems which say if it's projective and exchangeable, and basically it is this. So it's kind of, even definity is really surprising, right? You know, if it's exchangeable, that you get, you know, that it's basically just parameterized by this one p. That's amazing. So it turns out these things characterize more than you might think a priori.
And that exchangeability perhaps is a larger restriction than you might think.
Yes, absolutely, absolutely.
Okay, so I think questions can probably draw to a halt here, and I suggest we start 5 minutes after the hour so we do get a little bit of a tea break, so 5 minutes later than we're supposed to. And let's thank Christian again.